So obviously NASA and our partners in the aviation industry are concerned about our climate and the environmental impact of aviation. And aviation is critical to underpinning our economy. And so as we move forward into the next decades and century, we want to make sure that we're maintaining that economic competitiveness while also doing it in a sustainable way. And so we know that the carbon that's emitted from jet fuel is released and converted to carbon dioxide in the atmosphere, and that has a warming effect on Earth's climate. But what actually is surprising, and what the modelers are telling us, is that those line-shaped clouds that form behind the aircraft, or so-called condensation or contrails, may actually have a bigger climate impact even than the CO2 emitted from the engines. And so what we're trying to understand is, can we eliminate the contrails by switching to more sustainably produced fuels, as well as looking at more modern advanced technology engines? Today, the global supply of jet fuel is refined from petroleum-based sources. And so as we're looking forward, we need to get away from these fossil fuel-derived carbon sources and transition to a sustainably produced fuel that's derived mostly from biomass. And so this is a centerpiece of the administration's Sustainable Aviation Fuel Grand Challenge that brings together not only NASA, but all of the government agencies responsible for developing new fuels and developing the biomass and agricultural feedstocks that will be used to produce those fuels. NASA's role in the aviation community is to understand how new technologies and new fuels will affect the aviation fleet. And so while NASA's not producing the sustainable aviation fuels, we have the expertise both in the atmospheric science and in the aerospace world to understand how the sustainable aviation fuel will affect the engine operation and then translate into changes in climate-altering emissions. And so what we're doing with this project is an end-to-end investigation as we burn these 100% sustainable aviation fuels for the first time in some of the cleanest, most modern engines produced by CFM International. And we're going to measure the soot particle emissions from these fuels and relate them to the emissions from a conventional Jet A fuel. And so by understanding the reduction in soot, we'll be able to model that and improve our forecasts for how we expect emissions to change in the future from sustainable aviation fuel adoption. And so by studying the impacts of the sustainable aviation fuels, we're demonstrating their operability and their compatibility with the fleet, as well as the climate benefits that we can expect from these new technologies and fuels. By producing a sustainably produced aviation fuel that mimics the properties of that petroleum-based Jet A, we're able to have the best of both worlds and achieve not zero CO2 emissions, but net zero CO2 emissions. And so what we're doing is we're burning carbon that we've extracted recently from the atmosphere, and we're leaving those fossil fuels in the ground. One of the really cool aspects of this project is that it requires a tremendous amount of skill from our NASA test pilots, because they're not just flying a predetermined flight route. They have to get up there and judge for themselves, usually amongst a very complex cloud scene, where is the contrail, where is the plume, and how can I precisely put the DC-8 inlets and probes into the spot where the scientists need it to be. And so as they're working that skill to put the plane into the space we're measuring, the scientists are in the back watching the instruments, watching these strip charts showing the concentrations of carbon dioxide and particles. So it's a really big project, lots of different moving pieces, and so many different partners, each bringing a piece of their expertise to the table. And so that's what has made this, for me, so fun and so personally rewarding.
There's just a whole lot of unknowns when it comes to contrails, and data like this, or flights like this, allow us to gather that data to at least validate some of the initial hypotheses that are being bounced around in the scientific community. Sniffing is a word that always makes me laugh when I hear the scientists say it, but that's what they refer to when they're putting an instrument in the stream of an emission. They're sniffing it. Like we breathe in a different scent, the instrument is taking in those measurement or those particulates and the air and quantifying what it smells. So we sniff emissions. And the DC-8 just has so many different places that you can mount different instruments, and there are so many different instruments needed to quantify emissions that this plane is perfect.
The way that the mission works is when we take off, the Boeing aircraft takes off first, and then the DC-8 will take off just after, and then we spend the first 15 minutes of the flight coming up together. So we find out, everyone can see everyone so that we know how far apart we are and where we are in space with each other. And then once we know that, we come behind the Boeing aircraft and we're sampling back and forth across in their contrail. And we can do that roughly about 4.5, 5 miles behind them, as far back as 20 miles behind them. And as long as we have a general sense of where their contrail is, we can catch that without any issues. And we can sample all day long in that space. So the contrail is two parts, right? There's what we call the primary wake and a secondary wake. And the closer you are to the lead aircraft, those two wakes, they're right on top of each other. So we have to drop back further so that these two contrails, the primary wake and the secondary wake, are a little bit separated, and they separate vertically. So we're interested in about 4.5 miles or so where we can sample the secondary wake, which is the upper wake. And so from about 4.5 to 5 miles back, the pilots can actually see that, they can discern it, and they can see these two different layers. If we go down into the primary wake, there's a lot of turbulence, it can be dangerous for the aircraft that close. So we stay, that's what we call the midfield. We stay back about 4.5 miles, 5 miles, sample that secondary wake on top, and we come in and out of it. So as you can see the wake washes over the aircraft as you fly through the wake. And we do that because the scientists want to be able to collect data for 30 seconds or so, and then they want to pop out and get clean air so they can recalibrate their instruments, and then we go back in for about 30 seconds, and then we come back out. So it's like this all throughout the whole flight. And then we do something, after that we will drop back to the 20 miles or so, and at that point the primary wake has calmed enough that we can actually fly into it. So it's not dangerous for the aircraft anymore. So back there we're all over the place checking to make sure that the primary and secondary wake have the same kinds of characteristics. It's easier to sample a contrail when you can actually see it. Not all contrails are visible. In fact, most of the time they're not. So a contrail only forms when the conditions are just right. When the temperature is right, when the humidity in the air is right. As you're flying through, the engines will interact with those conditions to create the contrail. So it's a lot easier for the pilots to see when you can actually see the contrail. If we can't see the contrail, then we don't know whether or not we're actually collecting the data we're looking for. When we do all of our mission planning ahead of time, right, the day before, the day of, we're looking for very specific conditions somewhere within, the range of the aircrafts so that we can go fly in that area to, on purpose, create contrails that we can see.
It's like I say, it requires a lot more concentration than just normal flying from one point to the other. Yeah, so we split up the duties a little bit. While I'm over here flying and trying to position the aircraft in the right spot, concentrating mostly on the altitude and where we are left and right. Then usually I'm having the co-pilot control the power to keep my speed at about the same speed so that we stay the same distance behind the airplane in front of us. So I'm varying the altitude about 50 feet. So I'm trying to, plus or minus about 20 feet of altitude, which is very difficult to do in this very old airplane. So, but yeah, so I'll try to, get down a little bit lower so that it can get more of the stuff coming off of that primary wake mixed into the secondary wake. The reality is, I'm here to get them their data. So I have to put the airplane where they need it to be. So it's important for me to understand where they need it to be, you know, and important for them to understand the limitations of where I can actually put it. So.